Welcome. We shall now further look into the macroscopic balances. So, in this particular lecture, we shall be doing these concepts, that energy conservation in the integral form, some more things will be told to you, and how we can simplify this energy conservation for various types of cases. Then we shall look into the momentum balance, and we shall end up this lecture with some very basic applications of this mass balance, momentum balance and the energy balance. So, start with, let us look into the total energy balance, which already we have looked into our last lecture. It is just for recapitulation, because we are now going to simplify this form of equation by taking various kinds of assumptions. So, taking this as the basis, now we shall go to first assumption. Here it is. Now, if we can neglect the kinetic energy of the system, and when we can do that? We can do that if the flow velocity is very small. Okay? Perhaps then we can do that, or we say that there is hardly any change of the flow velocity along the flow direction. So, in that case we can take the change in the kinetic energy to be 0, or we can say that the it is itself is 0, change or the value itself is 0. And second assumption is that if the potential energy of the system is also 0, that means there is not a significant elevation of the system. So, in that case what we see, that neglecting the changes in the kinetic energy and the potential energy between the inlet and the outlet of the system, what we are left with is this, that we are left with the internal energy of the system, and that is given only in terms of the enthalpy of the ingoing and outgoing streams, and the heat interaction between the system and the surroundings, and the work. Okay? So, this is one simplification. Another simplification may come due to this. For liquid system specifically, it is not for gaseous system. Now, we see that we can write this U in terms of the enthalpy. Now, what we do, that we replace U by H minus PV. Now, this is a mathematical arrangement after this. Okay? Now, right hand side remains the same as we have done in the previous slide. Now, what we do is this, we now separate this particular integral into two. First we write dH by dt, and then minus dPV by dt, and rest of the things on the right hand side remains the same. Now, for the liquid systems, we find that P and V are generally constant. That means we hardly find much pressure drop in the liquid systems, and also because of the incompressibility of the liquids, we find that the change in the volume will not be also substantial, not significant. So, we may take out this particular term and make it 0, so that we are now left with the change in the enthalpy of the system in terms of the enthalpies going in and the enthalpies going out, the heat interaction and the work interaction. So, this is another kind of simplification to the system. Next, we come to another assumption, that is for liquid systems again. So, in this case we say that when the enthalpy varies insignificantly with pressure, that means we put that H, this is with respect to temperature, it is now varying. So, we find that we writing this H as Hk in terms of all the individual streams. So, what we can see, that the energy equation can now be written in terms of these enthalpies, which are now functions of only the temperature, okay, and they are now not the function of the pressure. So, this is something to do with the liquid systems. Another assumption we can do is this, enthalpies, this is again for liquids. So, in this case what we see, that enthalpies at the inlet, that is the feed conditions, and this we are giving by this, and the system conditions may be related like this. That means, this is the coming with the inflowing streams, and this is the actual system enthalpy, and they may be related like this, that for J stream at the Tj temperature. That means the J stream has the Tj temperature. As we said that we are neglecting the effect of the pressure on the enthalpy. Okay. So, HjTj is equal to HjT, and then we are putting this HjT is some kind of a datum value you can say, and that datum is taken as the system temperature, and then we are integrating CPdT we are doing from the system temperature to the temperature of the incoming streams. Okay. Because we know this relation is coming, because we know that the enthalpy is not having any absolute value, it is always dH, we write dH equal to CPdT. So, in this case we are just expanding that dH equal to CPdT in this way, that we are finding that at the feed condition or the conditions of the incoming streams, what is the enthalpy in terms of the enthalpy of the system. Okay. So, that is why we are doing it this kind of a manipulation. Now, we know that the specific heat can be taken to be constant for the liquids many a times. So, if we do so, then this particular integral will be reduced to simply Cpj into Tj minus T. Okay. So, this is another simplification we can do for the liquid systems. So, once we have done these simplifications, what we can do now, we can put it in the energy balance equation, and putting this kind of things, what we find that, see here we have putting only for the incoming streams, and the outgoing streams are taken to be same as the system conditions. So, these outgoing streams are having the same temperature as the system temperature. You can see this like this, that suppose you are having some kind of a liquid in a particular vessel, okay, and there is some liquid is coming from the outside. Now, that incoming liquid may have some different temperature, and if we are stirring the liquid within the vessel, the whole liquid within the vessel can come to a single temperature. Now, what happens? Whatever liquid you are now withdrawing from the particular vessel, you will find that outgoing stream will have the same temperature as the liquid which is inside the vessel. So, this is the way we see that the outgoing streams have the same condition as the condition of the system. Okay. So, that is why we are not putting there is no need to expand this outgoing stream enthalpy like the way we have done it for the incoming streams. Now, this is a special case for the reacting systems. Now, in the reacting systems, we shall see that enthalpy is a function of temperature, pressure and mole fractions. Okay. This mole fraction is given by mole is given by n, okay, and this moles for all the components C. So, we find that for any kind of system, this is the way we can write in general for the enthalpy. And now, if we take the time derivative of this, we know from our basic mathematics that how we write time derivative, that dH by dt will be equal to dou H by dou temperature into dt by dt. That is, this H is a function of the temperature and temperature is a function of the time. Okay. And similarly, this enthalpy is a function of the pressure and the pressure is a function of time, and this is the enthalpy of function of all the components moles, and this is the all the components moles are changing with time. Why? Because of reaction. Okay. Now, you see this dou H by dou Ni, what it means? It is the change of the enthalpy with respect to the change in the number of moles of a given component, keeping the number of moles of other components constant. Okay. So, in this particular thing we call it, this is the partial molar enthalpy for species I. Okay. This particular definition of partial property may be extended for any other property. So, this means that we keep the concentration of one species constant varying and other species constant at a given temperature pressure. okay, and this particular thing is replaced by this h over bar into I. Now, with this what we can do now, we can replace this with this h over bar, and many times for the liquids and ideal gases the enthalpy is independent of the pressure, so that we can write dou H by dou P is equal to 0. Next is that dou H by dou T, we know that dH equal to Cp dt. So, in that case we can write dou H by dou T as equal to the specific heat. So, with these kind of simplifications, now we can go back to this original equation. We can now see that dH by dt is equal to V rho Cp into dt by dt plus all these things. Okay. So, here we find that how the partial molar enthalpy and these things are coming. Please mind it, this V rho is coming why? Because this was a specific value. This was dependent per unit mass, and the total mass is nothing but the volume and the density. So, that is how we are getting the V rho term here. Now, we know that we wrote it in our previous lecture, the mass conservation in terms of the number of moles of the species, and here we have the same equation rewritten. So, we find that if we have this equation, we can again get after some rearrangement the following equation. So, this dH by dt, if you just combine this equation with this equation, you will find that dH by dt will be this particular term, that is the Cp delta T for with associated with all the incoming streams. Now, please understand, this is delta T, this is no more dt. Delta T is the finite difference between two particular values. Okay. So, here it is a finite difference between two temperatures, okay, and this is the one for the simplification we made in for the enthalpy of the incoming stream, and this is the reaction rate term. Here the reaction rate R is the reaction, that is the rate of change of moles of a species per unit volume. So, we have to put in terms of the we multiply this with the total volume to get the total change due to reaction, and total change, and you know that any reaction may be associated with some heat of reaction, and that heat of reaction will decide whether the system is exothermic, that is liberating heat, or endothermic, that is absorbing heat. Okay. So, this particular whole term signifies the total amount of energy change due to the heat of reaction, and rest of the things are as usual, that the heat interaction due to the conduction and radiation, and this is the work due to the expansion and the shaft work. That means, the only change we are extra term we are having is due to the reaction, and this will be absent when we have a non-reacting system. Now, you see this particular term is the difference between the partial molar enthalpies of the feed and the control volume at the control volume conditions, that is both are at the same temperature as that of the control volume. Now, this particular thing may be 0 for ideal mixtures, or may be very, very less than the total amount of heat that is generated for non-ideal mixtures. Okay. So, in that case we can neglect this particular term, and we are left with now this particular equation. Okay. So, that is another simplification we have made for the reacting systems. Okay. And this is the most common form of the energy equations, and you will see that we are using this kind of equations many a times. Okay. So, here are the ones that this particular term signifies the energy that is needed to bring the feed to the control volume conditions. Okay. That means, if the feed is at a lower temperature, then we need this kind of a sensible heat to raise its temperature, or if the feed is at a higher temperature than the control volume, then we need again a sensible heat to cool down the feed. So, this particular term represents that sensible heat, and this term represents the energy generation or consumption at the reactor conditions. okay, and this particular term represent the relevant heat and work terms. Okay. So, whenever we are making the simplifications, please do not forget to mention all the assumptions associated with the particular simplification. If you don't write the assumptions, then you are going to commit mistakes, and also please see to it that from system to system, from the process, different types of processes, which kind of assumptions are valid or not valid. Okay. According to the process, you decide that which assumptions need to be taken or need not to be considered, and that is why it is very, very important for us to understand the process properly. If we do not have a proper understanding of the process, the operating conditions, the thermodynamic properties of the various components associated in the process, then we are going to commit some mistake in the assumptions, and with wrong assumptions we shall be landing up with wrong results, and it will be giving us wrong analysis or wrong behavior performance prediction for the given systems, and will lead to wrong design for the systems. Okay. So, you have to understand all these concepts very carefully. Now, after looking into the energy balance, we now go to the momentum balance, and momentum, perhaps you know, that is another property that is conserved and is nothing but the product of the mass and the velocity. Okay. So, in general, the momentum is a vector, okay, because velocity is a vector. So, this momentum balance is important for mechanical systems where some flow takes place under the influence of various types of forces like viscous force, gravity force, electrical force, pressure force. So, there can be various types of forces associated with various types of processes in the nature. Okay. So, you have to consider appropriate forces. For example, if there is something coming down from some height, the gravity will play the effect. Okay. Viscous force comes when a fluid is moving over some surface, then due to the viscosity of the particular fluid, there will be some kind of drag force between the surface and the fluid, and the surface will try to retard the fluid motion. Okay. So, there you get this viscous effect. Similar effects you can also find when you are walking on some rough surfaces, for example sand. Then you will find, because there will be a lot of drag and it will be difficult for you to walk on the sand. On the other hand, the drag will be quite less if you are walking on some smooth surface or some ice. So, in the mountains when you go, you should be very careful on the whenever you are walking on the ice, because you may slip because of the very, very less amount of drag force on you. Okay. So, we know that this kind of drag forces are kind of a necessary evil at times to save us from any kind of calamity. But in case of this process also, similar manner, we find these drag forces generate some kind of pressure drop in the system. Okay. Now, let us go to the statement of the total momentum balance over a control volume. Here we have it, that rate of change of system momentum, and we are putting it this kind of m will be equal to rate of momentum into the system, that is given by m into this, not into this kind of subscript I in a parenthesis to signify the input, and this is the rate of momentum out of the system given by this kind of superscript, that is in parenthesis O. So, and the rate of momentum generation. Okay. Now, how do we generate momentum? This momentum is generated due to the forces. You know that rate of change of momentum is the force. So, any kind of force acting on the system will be generating some momentum change in the system, and that is how the flow behavior of the system will be different. So, this is the mathematical representation of the momentum balance, that dm by dt is equal to incoming momentum, rate of incoming momentum minus rate of outgoing momentum, and these are all the forces which are acting on the system. Now, after learning some basic concepts about the mass balance, energy balance and momentum balance, let us do a very simple analysis on a very simple system to see that how we can apply these concepts. So, let us for that we have this particular system here, you see that is a flowing system. In this case we are considering only one inlet and only one outlet. Okay. Now, we are doing what? We are having these two planes at the inlet and at the outlet, and we are considering that the inlet and outlet need not have the same area of cross section. So, we are representing these areas of cross section by A1 and A2 respectively, and we are having the fluid moving into the system with a velocity V1 and coming out of the system with a velocity V2. Okay. Now, to analyze this, first we apply the mass balance with some assumptions. The first assumption is that we are considering time smooth velocities, that means these V1 and V2 are, even if there is some small fluctuations, we are not considering that, we are taking an average velocity for these two at the two ports. Okay. And all properties including density are uniform over the respective cross section. That means, along this particular cross section here, we are seeing that there is no variation of the property. Okay. Similarly, at this cross section also there is no variation of property. So, in that case what we find, this velocity will be uniform, okay, at this particular inlet and this particular outlet, and these velocities are sometimes obtained from the division of the volumetric flow rate by the cross sectional area, and that is called the superficial velocity of the fluid. Okay. And we are also assuming that there is no consumption or generation. So, with these assumptions, we see that the mass balance between these planes 1 and 2 is reduced to this particular equation, and here we are simply having this mass content within the system is rho dV. So, the mass balance is coming to like this, that this is the total mass in the control volume rho dV. So, we are putting it like this, and here we have the two terms which are signifying the incoming and the outgoing flows, and here are the notations. We are putting the subscripts as per the particular port. So, 1 here represents the incoming port and 2 here represents the outgoing port. Okay. So, density into velocity into the area of cross section. Next we come to the momentum balance. It is also quite simple, that this is a rate of change of momentum and this is the rate of momentum into the system. How we are obtaining it? Here you see that rho 1 into V1 into V1. So, rho 1 into V1, that is density into velocity, is the rate of change of the mass. Okay. That means mass flow rate. Mass into the velocity is the momentum. So, that is m into v, or rho 1 V1 into V1 is the rate of momentum going into the system and into the area. Okay. And as you know, this is the unit normal that is coming out of the system. Okay. So, this is the mass flux into the area, that is giving me the rate of change of the momentum. Similarly, we have the mass flux as rho 2 into V2. Okay, there is the mass flux into area is the mass flow rate, and into the V2 gives the momentum. So, we are getting rho 2 V2 square into A2. Okay. And again this is associated with a direction, and this direction is given by the outward normal at this plane 2. Then we have the pressure forces, and for this equation please refer to in the previous lecture. So, we will see that this is the pressure force coming on the system and the pressure is acting on an area. So, pressure into area is the force. So, the pressure force at plane 1, and similarly we have the pressure force at plane 2, and again we have the unit normals associated at the each plane. Then we have the force due to the solid surface. As I was telling you, there could be drag forces which are experienced by the fluids due to the surface on which they flow, and next is the gravity force of the fluid. Okay. Now, let us go into the application of the energy balance for the same system. Now, in this case, please note that we have only two streams and we are naming them as F1 stream and F2 stream. F1 is the ingoing stream and the F2 is the outgoing streams. So, with each of these streams, we are associating all the kinds of energies we studied earlier, and now we are doing some simplifications on this particular system. So, first we assume that the system is at steady state. In that case, we find that there will not be any change in the energy of the system with time. So, that we are putting this left hand side derivative as 0. And also from the mass balance equation, we find that the flow rates will be constant from the inlet to the outlet, and there will not be any kind of accumulation of the mass within the system. Next, we make another assumption that isothermal system. In that case, we know that there will not be any change in the internal energy of the system, because internal energy is a function of only temperature. So, it will not be changing, so that the change in the enthalpy will be purely due to this change in this particular product P V, that P into the specific volume. Next, we come to another, that there is no energy or work interactions between the system and the surrounding. That is, neither we are giving any work to the system, nor we are trying to take out any work from the system. Okay? So, no pumping, no compressing, etc. So, in that case, we are putting the work interaction 0 and heat interaction can be put to 0 if we assume that the process is well insulated, so that it is adiabatic. Okay? So, in that case, we put the heat interactions to be 0. Now, with these kind of assumptions, we now write this particular expression, and now we find that U1 and U2 will be cancelling each other out, and what we shall be left with will be only these 3 terms and these 3 terms. Okay? Now, next what we do is that we write the expressions for the potential energy, the kinetic energy and the specific volume. We know the specific volume is the reciprocal of the density. Here we are writing the kinetic energy per unit mass, so that it is coming to half into V square. Similarly, the potential energy per unit mass is the product of the gravitational force and the Z. So, these 3 terms are now giving us the respective terms to be put in the energy balance equation, which we have just found out by making those assumptions. Okay. Now, we put those things here. We put that instead of the V cap, we are putting 1 by rho. So, it is becoming P by rho plus G Z plus half V square minus P by rho G Z plus half V square for the inlet and the outlet, and that is equal to 0. It means what? That if we take the difference, this delta is signifying the difference. So, that means the difference between the energy of the inlet and the outlet is 0, so that we see that the total energy in the system is remaining constant. That means there is no change in the energy from the inlet to the outlet, provided we have those assumptions we have just mentioned. And this equation, you are quite aware that this is the Bernoulli equation, and we say that this Bernoulli equation is the mechanical energy balance. Now, this mechanical energy, because all the terms in this particular expression does some kind of mechanical work. So, we are talking mechanical energy. Okay. Now, second thing is this, there could be various representations of the Bernoulli equation. Now, one representation can be, we divide the whole expression by the G. So, if we divide it by G, P by rho G plus Z plus half V square by 2G, the half V square by G. Now, what it means is this, that all the terms will be in some kind of a length dimension. Okay. So, whenever we are putting the various forces in or the energies in the length dimension, we call them head. So, accordingly, we have the various heads here. The first one, this one we call the pressure head. Pressure head. Okay. That means P by rho G, pressure head. So, you can check it also that when you take this P by rho g, the dimension will be in terms of some length. Okay. For example, if you are putting the SI unit, this will be meters. Okay. Similarly, if you look at this second term, now this will be only Z, it will give rise to only Z. Okay. So, this we call the potential head, that means it will tell us the effect of the elevation of the particular system from some given datum. So, this is the potential head. Okay. And the third term which we shall get from this particular term, this will be V square by 2 g. Okay. Again, if you take the dimension of this particular term, you will find this will be in terms of some length dimension. Okay. So, this we call the kinetic head. Okay. So, we have three heads. One I am writing again. Once we have the pressure head that is P by rho g. We have the potential head, that is simply Z, and we have the next is the kinetic head. And we find if we sum up these three heads, we are having constant. That means there will not be a total head of the system will remain constant, it will remain unchanged from the input to the output side. Okay. So, in this particular lecture, now we have seen that we have applied these energy balance, mass balance and momentum balance to a very simple system, and in future we shall do some tutorial on the various problems and to see that how else we can apply these equations. So, you can get more detail of this from these two books. They are very good books to give you more detail. Okay. And we shall also continue more on this in future. Thank you.